So today we'll discuss the relationship between the shear force and the intensity of load. So this is the today's topic, and to build up the relationship between shear force and the intensity of load, let me know the some symbol which we are going to use here. For the shear force we are using the symbol V, and the intensity of load, for this intensity of load we are using this W. This term we are using for the intensity of load. Now, to understand the relationship between the shear force and the intensity of load, we draw the simply supported beam having the UDL, uniform distributed load. When we apply this load onto this beam, so this is called the W, the intensity per unit length. So this is called the intensity per unit length, which we are denoting as a W here. This W, both are same. So W is nothing but intensity of load, unit per length. This intensity of load per unit length represented this UDL, uniform distributed load. So if I denote, this is RA and this is RB, the simply supported beam is there, R left to right. So in the simply supported beam, if you take this as a roller support and this is the pin joint or a hinge support, so the reaction will come here. So RBX, it can come. So to understand or to build up the relationship between the shear force and intensity of load, let me cut the small section at the mid of this beam. So this is say XX, the section we are cutting, and this is the X1, and this small distance which we are cutting here, this is called the DX distance, and this DX distance I'm just putting here, and the intensity is here, the distance is DX. So this is the distance and this is the load W per unit length we checked on this small beam having a distance dx. And if we move from right to left, the shear force we can here at this section, this is nothing but the summation of all the vertical forces only. So here the shear force at this section, I am writing this V. So this is the shear force, and if you move from this portion to dx distance, the shear force will be V plus dV, because some changes will be there. So I am denoting these changes as a V plus dV. And here this is, I am just pointing out as a upward force. So to balance this upward force, here the reaction will come which will be the downward. So that's why I'm just putting here this downward side, this force, and this shear force is nothing but V plus dV, because we move from dx distance here to here. So some of the forces will be there that I am counting as a dV, small changes in the shear force. And obviously because the reaction will be there, this because of the simply supported beam, and the UDL load try to bend this beam downward side. So this downward side will be a sagging. So because of this downward bending by this UDL and the reaction which tries to up this beam, so because of that the moment will produce in such a form, because this is nothing but a sagging. So sagging will be like this and bending moment will be like this in a sagging. So here similar pattern I am writing here, since it is a shear force, so bending moment I am writing as a M, and here of small distance dx, when we move the bending moment will be M plus dm. There may be small changes. So this bending moment I am writing as a M, bending moment symbol will be M. So this is the bending moment and shear force. So now the shear force, when we build up the relationship between the shear force V and this W, so we calculate the shear force is nothing but the summation of shear force is nothing but summation of all vertical forces only. So summation of Fy we are taking equal to 0. Since it is a UDL load, so this intensity will act at the centroid, at the center of this beam, which will be W into dx distance. So this UDL will count as a whole, because W per unit length means this load act per unit length. So W into dx length is there, so it is multiplying W into dx. So and this dx act in this beam at the center or centroid of this beam, so we are counting as W dx, and it acts downward of this beam, so we are writing as W into dx. Now here we are counting the summation of all vertical forces for the shear force. So all vertical forces we are counting here. This is the upward force V, and our sign convention is that when we move right to left, downward direction force we are taking positive, as already we have discussed in our previous lecture. So downward force we are taking positive, and upward force we are taking negative. So this upward force we are taking as a negative V, and W dx, which is positive because downward act, W into dx, and here this V plus dV shear force is positive because downward is there, V plus dV. The moment will not be counted, because for the calculation of the shear force only the vertical forces we count, that is equal to 0. So here V cancelled, and W into dx plus dV equal to 0, or this we can write, this we can shift here, dV by dx equal to minus W by solving this equation. So this is nothing but the relationship between the shear force and intensity of the load. So this shear force is nothing but the rate of change, this is called the rate of change of shear force with respect to x is equal to the intensity of the load. Now we can write here, shear force is nothing but rate of change of shear force with respect to x. X is nothing but location of section, this is x. So this dV by dx equal to minus W is nothing but rate of change of shear force with respect to x. This rate of change of shear force with respect to x is equal to the intensity of load, is equal to the intensity of load. Means the rate of change of shear force, dV is nothing but rate of change of shear force with respect to this x is equal to intensity of the load. Or in the another word we can write the slope, this is very important, slope of the shear force, curve at a given point is equal to minus the distributed force. Means this slope dV dx nothing but slope of this the shear force curve at any given point of the beam is equal to the minus of this distributed load. W is nothing but the distributed load or intensity of load. So this is the another definition for this shear force. So here the shear force and intensity relationship is nothing but this dV by dx equal to minus W. This is very important when we solving the problem related to the shear force and bending moment diagram having the UDL load or this UVL load, this uniform varying load. So is at center C. Okay, so this is the moment M, shear force V, and here shear force V plus dV, and moment is M plus dm. So this is the dx again, here to here, this is dx by 2. Because this w, the intensity of w act at the center of this beam at dx by 2 and dx by 2 distance. So here we can take the summation of moment at a c equal to 0. So we can take all the moment. So here, from here we start right to left, we move right to left. So right to left, because this is called the sagging. So here in sagging, the bending moment which move it up will take positive. So this m we are taking positive, this, and then we try to up this beam, so it becomes a sagging. So because it's moving anti-clockwise and try to move up the beam, so we are taking this positive v into, because moment we are taking at point c, so v into perpendicular distance is nothing but dx by 2. Then here this v plus dv, when we are taking a point c, this moment, so v anti-clockwise it move because direction is anti-clockwise, and it try to up the beam, so it will be positive. So v plus dv positive into dx by 2, and then this m plus dm, because it moves clockwise and it try to bend this beam downward side, so it will be negative m plus dm, that equal to 0. Now this m plus v into dx by 2 plus v into dx by 2, when we open this bracket, dv into dx by 2 minus m minus dm equal to 0. Here m will be cancelled, since this dv into dx by 2 is such very small value, because the product of these two is small, will be very small. So because of this very small, we neglect this value. So remaining will be 2 into dv dx by 2 minus dm equal to 0, or if you cancel this, so it will be v into dx minus dm equal to 0, or dm by dx equal to v. Now what is the meaning of that? The meaning of that, the rate of, we can write rate of change of bending moment will be equal to shear force. Now here you can see that the rate of change, dm is nothing but rate of change of bending moment with respect to x. This with respect to x equal to shear force, means dm by dx equal to shear force. Rate of change, this dm by dx is called rate of change of bending moment, will be equal to shear force, or in another word we can write the slope of the bending moment, the slope of the bending moment curve at a given point is equal to shear force. Okay, so is equal to, you can, this is nothing but equal, so this equal to shear force. So this is the all about the relationship between the shear force and intensity of load, and the relationship between the shear force and bending moment. So this